Welcome to ASU's University Academic Success Programs. This video will cover the topic, Gauss's Law of Electric Flux. Flux describes an amount of volume flowing through an area in time. Here's a great example of flux. Imagine holding a hoop of wire in front of a fan. The volume of air flowing through the hoop per second is the flux of the air. Now we are going to describe electric flux. Electric flux measures an electric field passing through a surface area tilted at an angle theta from the field. If the field is uniform, then the flux is phi sub E, which is the symbol for electric flux, equals E dot A. And the magnitude of the flux is phi sub E equals EA times cosine of theta in units of newtons meters squared per coulomb. And remember, theta is the angle between E and A. Now, if the electric field is non-uniform over an unknown area, then the flux is an enclosed surface integral. Phi sub E equals the enclosed integral of E dot dA, where this time E is a function and dA is a differential element of area.
So how can we use electric flux in our physics problem?
Great question. Once we learn Gauss's law, we will be able to relate flux with electric charge and use this to solve for needed values. So here is Gauss's law. Phi sub E, flux, equals the surface integral of E dot dA, which we just learned is the non-uniform version of flux, which is equal to Q enclosed, which means charge, divided by epsilon naught. Now this is the general form of Gauss's law. For a uniform field, it is usually simplified to flux equals EA cosine theta, which is equal to Q enclosed over epsilon naught. So Gauss's law means that the flux coming out of an enclosed surface is equal to the total charge inside the surface divided by the permittivity of free space. And here's just a quick reminder that the permittivity, epsilon naught, equals 8.85 times 10 to the negative 12th coulombs squared over Newton meters squared. So if we have one point charge with a charge of Q, this describes the flux of this point charge. Or this describes the flux of a closed surface with several point charges added together.
Okay, so these are all forms of the equations. Can we do some examples of just flux alone?
Of course. We'll do one example showing the formula EA cosine theta, and then we'll do an example where we can use Q enclosed over epsilon naught. Let's say we have a 3 meter by 4 meter rectangle tilted up 20 degrees, with a known electric field E of 50 newtons per coulomb going straight into it. What is the electric flux into the rectangle? If the rectangle is tilted 20 degrees, and we say the area points directly out of the rectangle, then the angle between the electric field and the area is 70 degrees. Remember that the formula for flux is EA cosine of theta. Let's substitute in our given numbers. Flux equals 50, which represents the electric field, times 3 times 4, which is the area of the rectangle, times cosine of 70 degrees, which is the angle between E and A. After calculating this, we find electric flux equals 205.2 Newton meters squared per coulomb. Now let's do another example. Let's say we have this closed surface with inside charges Q1 equals 5 nanocoulombs, Q2 equals 3 microcoulombs, Q3 equals 10 nanocoulombs, and Q4 equals 2 picocoulombs. What is the electric flux coming out of this shape? Here we use the formula flux equals Q enclosed over epsilon naught. We have to add all the charges together to find Q enclosed, and then we can divide that by the permittivity constant. Q1 converted to coulombs is 5 times 10 to the negative 9th, plus Q2 converted to coulombs is 3 times 10 to the negative 6th, plus Q3 converted to coulombs is 10 times 10 to the negative 9th, plus Q4 converted to coulombs is 2 times 10 to the negative 12th. After adding all these together, we find that Q enclosed equals 3.02 times 10 to the negative 6 coulombs. Now we will substitute this into the formula. Flux equals 3.02 times 10 to the negative 6th divided by 8.85 times 10 to the negative 12th. And after performing this calculation, we find electric flux equals 340,678.2 Newton meters squared per coulomb.
Okay, now that we have done some examples of electric flux, how can we use Gauss's law to our advantage?
Perfect question. Finding the electric field of a point charge is not very difficult. But in some problems, we will have a distribution of charges, and we will be asked to find the electric field of that at a certain point. To do this, we have to integrate individual sections, which becomes challenging. However, if we have a uniform distribution of charge on a symmetrical shape, such as a sphere for example, we can use Gauss's law to find the electric field without having to use integral calculus. Imagine a conducting sphere of several point charges, and we are asked to find the electric field strength coming from the sphere at a point 25 centimeters away from the sphere. This sphere is a uniform distribution of charge, so the electric field points uniformly outward from all points of the sphere. Therefore, we can draw what is called a Gaussian surface to use so we can find the electric field without setting up an integral. A Gaussian surface is an imaginary mathematical shape that mimics the shape of the charge distribution. In this case, it will be a sphere concentric to the conducting sphere on which the point we are asked to find the electric field is present. In other words, it is an imaginary sphere of radius 25 centimeters with the conducting sphere as its center. In the equation, flux equals EA cosine theta, which is equal to Q over epsilon naught, the surface area of the Gaussian sphere is the A. Now let's say that the three charges inside the sphere are Q1 equals 3.0 nanocoulombs, Q2 equals 5.0 nanocoulombs, and Q3 equals 9.0 nanocoulombs. Again, the goal of this problem is to find the electric field at the point 25 centimeters away. And because the angle between E and A is 0, cosine of 0 equals 1, so therefore we will not deal with the angle in this equation.
Now that we have gathered all this information, what should be the first step that we take?
The first step that we'll want to take is to use algebra to find E alone on one side of the equation. We'll divide both sides of the equation by A to find E equals Q enclosed over A times epsilon naught. Now that we have done this, we will substitute our numbers in to solve for E. Remember that A of a sphere equals 4 pi r squared, and r equals 25 centimeters, which converts to 0.25 meters. And the charge Q is the sum of the three charges. So, E equals 3.0 times 10 to the negative ninth, plus 5.0 times 10 to the negative ninth, plus 9.0 times 10 to the negative ninth, all divided by 4 times pi times 0.25 squared times 8.85 times 10 to the negative 12th. After performing this calculation, we find E equals 2,446 newtons per coulomb. This is our final answer. Now note that there are several other types of Gaussian surfaces and several other types of problems for this topic, which should all be discussed in your class. It takes a good amount of practice to effectively master Gauss's law, but once you do, it becomes a very useful tool in electromagnetics.
Okay, so what I am understanding from these examples is that electric flux can be found if the electric field, surface area, and angle are given. It can also be found from an object if the charge of the object is known. If we have a uniform charge distribution on a symmetrical shape, we can draw a Gaussian surface around the shape that is similar to the shape and use its surface area and Gauss's law to solve for electric field or charge. This can save us the time it would take to set up an integral. However, if the electric field is not uniform, we would have to set up an integral.
Very good summary. It sounds like you are now ready to apply Gauss's law.